today we're going to talk about heat diffusion and heat of vaporization and how these affect phase changes and some calculations that we're going to be doing with them that I like to refer to as Q calculations. Heat diffusion is the amount of heat needed to convert a mass of a substance from solid to a liquid. You can actually see, if we just go back for a minute and take a look at a heating curve, the heat of fusion is actually this heat that we're putting in here when we have a phase change occurring, but we do not have a temperature change occurring. So the heat of fusion is really like an amount of energy that allows for that change in potential energy, that molecular rearrangement. So if we think about a sample of ice, in order to melt that ice, we have to break these intermolecular forces. So these little, what we call hydrogen bonds, which we'll talk about later, they hold ice in its crystalline formation. In order to turn ice into liquid water, those have to be broken. In order to freeze a sample of liquid water, these new forces must be formed, and the exact same amount of energy is actually involved in that transition. So again, as I mentioned before, if we look at a heating or cooling curve, we can see this flat region in the graph where we're putting in energy, and we have a change in potential energy, but our kinetic energy is remaining the same, as we see, because we have no temperature change. So that potential energy increasing has to do with intermolecular forces being broken. So we'll actually be doing some calculations with these. If you could flip to table T on your reference table, the phase change between a solid and a liquid, energy calculations can be done using the formula Q equals mHf. If you look at your reference table, it'll tell you that Q is heat. If you flip back to table D, heat is in a unit called joules, which I'll represent by a J. M stands for mass, which as usual is in grams. And HF is something we call the heat of fusion. This is this amount of energy that it takes to cause this phase change to occur. And that's in the units of joules per gram. The value for heat of fusion for water can actually be found on table B. So for freezing, fusion, melting, solidification, anything where you're going from a solid to a liquid or a liquid to a solid, this calculation, this formula can be used. The amount of energy that you calculate, if you're going from a solid to a liquid, that's what you would add to the sample. A liquid to a solid, that's what you would remove from that sample. So if we wanted to calculate how much heat is needed to melt a 200-gram sample of ice. So because we hear that word melt, that's how we know we're going to be doing a heat of fusion calculation. So what I know from the problem is that the mass of the sample is 200 grams. And I also know that we're talking about melting. So therefore, I'm going to be using my heat of fusion. And I can find that on the front page of my reference table. It's 334 joules per gram for any problem where we're involving water. And ice tells us this involves water. We can do these for other substances that heat of fusion would have to be given to you. We want to solve for Q, which means heat, and that's going to come out in joules. So we're using Q equals mHf. I'm going to go ahead and plug in our values. Our mass is 200 grams. Our heat of fusion is 334 joules per gram. So you're simply going to multiply these two numbers. And when you punch this into your calculator, you're going to notice, wow, that's a pretty big number. And you might kind of say, ooh, why is that so big? It's actually okay to get a large answer for this. A joule is actually a very small amount of heat. So if I were to say to you, hey, how many inches are between here and New York City? Your answer would be a large number of inches. The amount of energy that we're talking about here really isn't that crazy. It's just joules are actually a pretty small amount of energy. So it comes out to a very big number. Sometimes we like to change joules into kilojoules, but it's often easiest to just leave it in joules. You will notice we kept 3 sig figs. We've got 3 sig figs right here. So we have 3 sig figs in our answer. Try another problem. If 167,000 joules of heat is needed to melt a sample of ice. What is the mass of the sample? So this time we know our Q. We know we are melting. So that tells me this is an HF problem. And I just go back to the reference table B again. And I'm going to identify my unknown, which this time is going to be mass. It will come out in grams. So again, we're using Q equals MHF. Plug in your heat on the left-hand side, M for mass, and 334 joules per gram for our heat of fusion. And this time we are going to be dividing. So you're going to do 167,000 divided by 334, which should give you about 500 grams of water. You should have 3 sig figs, which is why I have that decimal there. That makes those zeros count as significant figures. The heat of vaporization is a very similar concept. The heat of vaporization is the amount of energy that it's going to take to convert a mass of a substance from the liquid or gas state. So we have these same interactions between water molecules and the liquid state. If we want those molecules to become a gas, those interactions have to be broken, and this requires a significant input of energy. If we want to form, so if we want to condense a vapor, these forces have to be formed, so we have to remove energy. Again, it requires potential energy to break these intermolecular forces. It's an input of energy. In order to cause these forces to form, we actually are removing potential energy, or potential energy gets released. The amount of energy involved is actually much larger typically. So if you look at region D on the graph, this would be your heat of vaporization right here. Heat of vaporization for a substance is usually much, much greater than the heat of fusion, and you'll see that's true for water. It actually takes a ton of energy to get the liquid state to get those molecules to move far enough apart to then be in the gaseous state. So right on reference table T, right near the rest of your Q calculations, you'll see one that says Q equals MHV. This formula works exactly the same. We have Q for heat, again in joules, M for mass in grams, and we have what's called the heat of vaporization in joules per gram. And again, that's look-upable on table B. So this is what we're going to be, if you see the words boiling, evaporating, vaporizing, condensation, this is the amount of energy that would either be added to the sample to go from liquid to gas, or removed from the sample to go from a gas to a liquid. So, try one of these problems. How much heat is needed to vaporize a 200-gram sample of liquid water? So we're dealing with water. We know we're vaporizing. They're telling us we have a mass of 200 grams. The fact that we see the word vaporize tells us we're going to be using HV. So you're going to go to reference table B. It's 2,260 joules per gram. So that's much greater than your heat of fusion. Our unknown here is going to be Q, which will come out in joules. So this is essentially a very similar equation. You just have to make sure that you're plugging in the right value for your heat of vaporization. Don't get confused and accidentally plug in the heat of fusion. It's actually a very common mistake. So we're going to multiply our mass of 200 grams times our heat of vaporization of 2,260 grams. And this gives you a rather large number, 452,000 joules. Now, if you compare this to what we did in this problem, we actually had the same mass, but we were only melting here. That's a much smaller amount of energy. So it does show that it takes a larger amount of energy to turn the same quantity of liquid into a vapor as opposed to turning a solid into a liquid. So we'll do one more sample problem. At 113,000 joules, sorry, 113,000 joules of heat is needed to vaporize a sample of water. What is the mass of the sample? So again, we're going to make Q here. You see the word vaporize. Our unknown in this case is mass. We're using Q equals mHV. So again, we're going to be dividing here. 113,000 divided by 2,260. And this gives us a mass of 50 grams of water. And this should actually have, 3 sig figs in it. So this should actually be, with proper sig figs, 50.0 grams. And that is where we're actually going to stop for the day. I just kind of like this graphic that shows that transition whenever you're going from a solid to a liquid. That's when you would use your HF calculations. So this is Q equals MHF, and this is Q equals HV to go between a liquid and a gas.